Hi folks, Mrs. Gates here. Today we are going to be talking about the force of friction. Our main goal is to come up with an equation or a way to calculate how big the force of friction will be in various situations. Let's get started. Let's start with a warm-up question. Here we have a man pulling a large crate across the ground. He's pulling the crate at a constant velocity and exerting his force through a cord that is making a 30-degree angle above the horizontal. Start by sketching a force diagram for the box. Pause the video and take a moment to complete your sketch. Your diagram should have looked something like this. You have the force of gravity pointing down and the normal force pointing up. The force of tension, or maybe you called it the pull force, should be pulling up and to the left. I sketched in the component vectors for that force, showing that part of the pull is to the left and part of the pull is going straight up. There is also going to be a force of friction on this box. How do we know that there is going to be a force of friction? Well, because he is pulling the box at a constant velocity, that tells us that the net force on the box has to be equal to 0. Since one part of the pull force is going horizontally to the left, there must be something pulling in the opposite direction to balance that force out. In this case, that force is the force of friction. Take a moment and now look at your force diagram. Which of the force pairs listed here must be equal to one another? Pause your video while you think. The two forces here which must be equal to each other are the force of friction and the component of the pull force that is in the x direction. These are the only forces that are acting in the horizontal direction, and since the box is at a constant velocity, they must be equal to each other. If we consider the forces in the vertical direction, we look at the forces going up, the normal force and the force of tension in the y direction. Added together, these two forces must be equal to the force of gravity. This is one of our cases where the normal force is not equal to the force of gravity on an object. When you consider the force of friction, do you usually think about it as a positive thing or a negative thing? Often we think of the force of friction as a negative thing. It slows us down, it makes things difficult, it heats things up. But there are a lot of cases when friction is actually quite useful. For example, have you ever tried walking on slick ice? This is one time when you remember how useful it is to have some friction between your feet and the ground. Friction is also helpful when you're trying to drive a car. Without friction between the tires and the road, your car can't get much of anywhere. Or it gets a lot of somewhere, but not the somewhere you'd like it to be. Friction is helpful when we're trying to brake, whether we're braking a car or a bike. The thing that slows us down in a helpful way is usually friction. And it's helpful when we engage in sports, such as climbing. As we consider how we might find a numerical value for the force of friction, let's think back to the lab you did about the force of friction. Part 1 of that lab investigated static friction. Recall that static friction is the resistive force between two surfaces when they are not sliding. If the object is motionless, the force diagram would then look something like this. The force of the push or the pull going to the right and the force of the friction going to the left. Newton's first law tells us that if the object is to remain motionless, the net force on that object must be equal to 0. That means that the force of friction must exactly balance out the horizontal component of the push force. When we saw that the force of friction matched the applied force, we ended up sketching a graph that looked something like this, where the friction increased up until the point where the object began to slide. Once the object began to slide, we were then dealing with kinetic friction. Kinetic friction is the resistive force between two surfaces that are sliding relative to one another. Once the object started to slide, we noticed two different things. The first thing was that the kinetic friction stayed constant no matter what push force was applied and no matter what the object's speed, as long as it was moving. The second thing we noticed was that the kinetic friction was less than the maximum force of the static friction. So the graph we drew in our lab looked something like this. Once the object began sliding, the force of friction stayed constant and was slightly less than the maximum force before the object began to slide. Now, if we think about what this means for calculating values for the force of friction, when we talk about static friction, the force of friction will always equal the force applied, up until the point where it begins to move. This point we can calculate using an equation that looks like this. The force of friction equals the coefficient of friction multiplied by the normal force. There are a few things to note in this equation. The first thing is this strange backwards looking U symbol. This is the Greek letter mu and is the symbol that we use to mean the coefficient of friction. Here we've put a subscript s next to it to signify that this is the coefficient of static friction. The coefficient of friction is a number between 0 and 1 that simply describes the roughness of the interaction between two surfaces. Ice sliding on ice will have a low coefficient of friction, but rubber scraping against concrete will have a high coefficient of friction. The second thing to notice about this equation is that the force of friction depends on the normal force between the two objects. You may have expected that the force of friction would depend on the force of gravity or the weight of an object. Let's look at an example to see why that is not the case. Imagine a box sitting on the ground. The forces acting on the box would be a force of gravity, or the object's weight, and the normal force pushing up from the ground. Now imagine that we begin to pull on the box. Imagine that our pull force is the maximum amount of pull that we can pull before the object starts sliding. Let's imagine one more thing. Let's say that someone pushes down now on top of this box. Well, we would expect that pushing down on the box would increase the amount that we could pull before the box would slide. It would increase the maximum amount of static friction. Why? The force of gravity hasn't changed. This is because the force of friction depends on the normal force. When someone pushes down on the box, they are introducing an additional vertical force. That means that to compensate, the table must push up with a greater normal force on the box. When the normal force increases, the maximum force of static friction also increases. That is why the equation for the maximum amount of static friction depends on the coefficient of friction and on the normal force between the object and the surface that is providing the friction. Now that we know how to calculate the force of static friction, let's consider kinetic friction. Recall that kinetic friction was always the same value and plotted with a horizontal line on our graph. The question is, what is the value of kinetic friction? Well, just as the maximum static friction depended on the coefficient of friction and the normal force, the force of static friction also depends on the coefficient of friction and the normal force. In this case, we have written a subscript k next to the mu to signify that this is the coefficient of kinetic friction. In the same way, the coefficient of kinetic friction is a number between 0 and 1 that describes the roughness of the interaction between two surfaces. This chart shows some values for the coefficients of static and the coefficients of kinetic friction. Consider the numbers shown here. In general, which is higher, the coefficient of static friction or the coefficient of kinetic friction? Which surfaces have the most friction? Which surfaces have the least friction? Considering the values in this table, you can see that the Considering the values in this table, you can see that in general, the coefficient of static friction is greater than the coefficient of kinetic friction. That makes sense if you consider the result we found that the maximum static friction is greater than the force of kinetic friction on an object. The surfaces that have the most friction between them are rubber on concrete. That also makes sense as this is what tires are made of to give them maximum grip on the road. The surfaces that interact to have the least amount of friction is ice sliding on ice. Let's look at an example to help us practice using these equations. Let's say we have a 5-kilogram box, that is a box which weighs about 50 newtons, sitting on the floor. In order to get the box moving, in order to overcome static friction, we need to apply a 20 Newton horizontal force on the box. First, draw a force diagram for the box when this 20 Newton force is applied. Then, use the values from your force diagram to calculate the coefficient of static friction between this box and the ground. Pause the video to work out your answer. The force diagram you drew should look something like this. Both the force of gravity and the normal force here are 50 newtons. The push force to the right is 20 newtons, and the force of friction for the maximum static friction is also 20 newtons. Recalling our equation for the maximum static friction, we can plug in that the force of friction was 20 newtons and the normal force was 50 newtons. Dividing 20 by 50 gives us the coefficient of static friction, which in this case is 0.4. Notice that we divided 20 newtons by 50 newtons, and the units newtons canceled out. The coefficient of friction has no unit associated with it. Let's look at an example for kinetic friction. Here we have the same 5-kilogram box, which weighs 50 newtons. Let's say that once it starts sliding, it takes 15 newtons of force to keep it moving at a constant speed. What is the coefficient of kinetic friction between this box and the ground? Take a moment to draw a force diagram and calculate your answer. The force diagram that we have in this case is very similar to in the previous case. Since the block is moving at a constant speed, the forces must be balanced. That means that when we have a pull force of 15 newtons, the force of kinetic friction must also be 15 newtons. Looking at our equation for kinetic friction, we can plug 15 in for the force of friction and 50 in for the normal force. Dividing, this gives us a coefficient of kinetic friction of 0.3. Again, no units on the coefficient of friction. Now, using the relationships shown in this graph, as well as the equation shown here, you should be able to calculate the force of friction in almost any situation. Happy physicsing and have a great day.